In the last several sets of slides, we've learned a lot about matrices and matrix multiplication, and we're going to put the power of all that stuff to work in helping us solve systems of linear equations. Most of that's going to happen in Unit 2, but for now we're just going to take a look at linear systems, systems of linear equations, before we get into all the matrix stuff, and we're just going to ask some simple questions like, well, what the heck is a system of linear equations? What do we mean when we're talking about solutions to those systems? And is there some sort of predictability about the types of solutions we might expect given the way the system looks to begin with? So, before you have a system of linear equations, you have to know what a linear equation alone looks like. This is the fancy way of writing one out. So in this expression, there's variables called x1, x2, all the way down to xn. Right? Could be x5, it could be x10, whatever. And then each of those is multiplied by a constant. The important thing to note is that each power of the variable is just the first. And there's only constant multiplication of all the terms that are then added up. So lots of variables raised to exponents 0 or 1. And the 0 exponent is hiding in the last term. So a0 is technically the same as a0 times a variable x0, where x0 is raised to the 0 power. That's a technical detail, but it's there. And sometimes we're going to enumerate variables like x1, x2, x3, and other times we're just going to name them different letters like x, y, and z. It doesn't really matter. Okay, so here's some equations on the screen. Some of them are not linear equations. So to be linear, all the variable powers have to be to the first or just have constant terms. You can't have products of the variables. You certainly can't have roots of the variables or anything like that. So take a look, pick out the ones that are not linear equations. And it turns out that it's the second and third in the first column, and that's it. These two right here are not linear. This one is not linear because of the product xz. X, y, and z are variables, but because there's a product term x times z, you can't have that for a linear equation. Down here in the lower left-hand corner, x1 and x2 are both being squared. That spoils it for being a linear equation. And I've tried to trick you. See, over here in this equation there is a square root, but be careful. That's the square root of 2. That's just the constant. x4 itself is still only to the first power, so we're fine. This is actually a linear equation. Here is a linear equation, and it's a simple one. 2x minus 6 is 0. You've seen these before, and you can tell me if x equals 3 is a solution to this equation. It most definitely is, because when we plug in x equals 3, we get a statement that is true. Are there any other solutions to this equation? No, there are not. You know how to do the algebra to solve for x, and you would come back with x equals 3 and only that. Here's another linear equation. This one happens to have two variables in it. 2x minus y equals 4. One linear equation. Is the pair 0, negative 4 a solution? Well, we test it. We plug in 0 for x, negative 4 for y. If we do that, we get 0 minus negative 4. Ta-da, that's 4. This point is a solution to that equation. Are there others? Well, yes, there are many others. Right? You can test those points individually. Each of them actually provides a solution to that one linear equation, 2x minus y equals 4. So we had one linear equation that had one and only one solution. Next we had one linear equation that has lots of solutions. What's different? Interesting. Now a system of linear equations is what you get if you take a bunch of linear equations and put them together and say, hey, consider these as a package. Which one of these two on the screen is not a system of linear equations? Well, it's the first one, because x1 is squared in that first term there. So that spoils this equation. It's not linear, so it can't be. The second equation isn't linear. The system can't be linear. The bottom one is. If you have a system of linear equations, several linear equations bundled together, a solution to the system is the point or points that make all of the equations work at the same time. So here is a system. Two equations with two variables. Is the pair 2, 0 a solution to the system? Well, to check that, you take x equals 2 and y equals 0, and you plug them into both equations and make sure that both statements become true. And if you do that, you will note that both work. Right? If you plug x equals 2 and y equals 0 into the top equation, it works. We saw that on the previous screen. With this new equation, if we plug in x equals 2 and y equals 0, we get 2 plus 0. That's 2. The second equation works. This is a solution to this system. Are there others? Well, in this case, no, there aren't going to be others. Now, I'm not telling you how I know that. You might know that. I'm just telling you the facts at this point. So this system has a solution. It does not have other solutions. But there's something interesting to note, that this is two equations with two variables. Here is two equations with two variables. Let's check the point 20 again. Is this a solution to the system? Well, one more time, plug in 2 for x and 0 for y in the first equation, which is the same first equation as it has been. That works. But if we plug in 2 for x and 0 for y down here, we will get 8x minus 0, and that's not 4. So this point doesn't work for the second equation, which means it doesn't work for the entire system. It has to work for all of them. So this is not a solution. Are there others? Well, no, it turns out there aren't any other solutions. So here's two equations with two variables that doesn't have any solutions at all. Either one of the individual equations will have plenty of solutions. Put them together, look for points that satisfy both of the equations at the same time, you're not going to find any. And so here, two equations, two variables, but now no solutions, and oh man, that starts to spoil any sort of general conclusions we were trying to make. Dang it. All right, here's a solution of linear equations. Something good's going to happen here, I can tell. Same first equation, different second equation. 20, as we know, satisfies the first equation, and ta-da, now 20 does in fact satisfy the second equation. So that point is a solution to this system. Are there others? Yep, there's lots. So two equations, two variables. We've seen this have one and only one solution. We've seen a system like this have no solutions, and now we're seeing a system that has tons of solutions. So, yeah, there's no rules. Well, okay, there is a rule. We've looked at the three different possible cases, though. So if you have a system of linear equations, that system will have no solutions, it will have one solution, or it will have infinitely many solutions. So if you're looking at a system and you've found it has no solutions, fine, you're done. If you found that it has one and only one solution, fine, you're done. If you found that it has more than one solution, then what you found is it will actually have infinitely many solutions. You're not going to stop at 5 or 10 or 500. If it's more than one, it goes right to infinitely many. Okay, here are some other rules, and it'll take you a while to get used to these. If the number of variables is more than the number of equations, there's not going to be just one unique solution. There could be none, there could be infinitely many. And when you do find out that your system has infinitely many solutions, you don't just say, hey, there's infinitely many solutions and be done with it. You actually still find the prescriptive nature of the solutions because there will be a pattern, and you have to discover that pattern and present it. Because infinite solutions doesn't mean everything's a solution, so you still need to know how do you determine points that are versus points that are not solutions. Everything we looked at, we were looking at examples that were 2 by 2 systems, 2 equations, 2 variables. But they hold for all the rest. Okay, so here's the system we saw that ended up, we discovered 4 solutions, so now we know that it will have an infinite number of solutions. We have to provide a recipe. And so what we can notice here is that there's a pattern, and that pattern is the y-coordinate is 2x minus 4. Check that for all 4 points. You'll see that it's true. The y-coordinate is twice the x-coordinate minus 4. And so that means that we could go and generate lots more points in this solution set by just picking an x-coordinate and then calculating 2x minus 4 out of that x-coordinate, and that pair will then provide yet another solution in our list of infinitely many. And so this is how we want to be able to present solutions in the case where there's infinitely many, is to provide the recipe. Now again, I have not told you how we make this distinction and how we discover them from scratch. I've just provided examples and cases. That's what's going to come up in the next unit, which is how we're going to bring back the topic of matrices and learn how to solve these systems of equations and find out about their systems and their solutions from scratch.